We are on the fourth lecture of our fluids unit, out of 6 lectures, so you have finished more than half of this at this point, which is good. Um, Buoyancy and Archimedes' principle is going to be a lot of force balancing, so we will talk a lot about that before we start talking about fluids that are going to be actually in motion. So our learning targets, I can define buoyancy and buoyant force, and so you've probably heard of the word buoyancy before. Probably not something new, but we'll definitely talk about it in terms of physics. I can explain Archimedes' principle. That might not be something that you've heard of before, unless you did like a really brief overview of it in like physical science in middle school or something like that. I could solve problems both qualitatively and quantitatively involving buoyancy and Archimedes' principle. I could define specific gravity, another thing that you may have touched upon in either chemistry or some kind of physical science in middle school. And then I can explain how gravity is related to density. So, earlier we saw this image here when we talked about pressure and defined pressure. So you might have noticed that the arrows here are all pushing down on the top of the submerged object are shorter than the arrows that are pressing up on the bottom. So there is actually a reason for this. So you can see that these lines here are in fact shorter than these lines here. So because pressure due to a fluid increases with depth, there's going to be a greater pressure at the bottom of the object than at the top. Okay. So if an object is submerged in a fluid, there's going to be a net force that is directed upwards on that object because the pressure is greater at the bottom than at the top of the object. And that is what we call buoyant force, which we are going to derive because I know how much we love deriving things. 1 second. I forgot to share my screen on Zoom so that I can actually write on this. There we go. Okay. So let's derive this really quickly. So buoyant force is going to be the difference between the two forces of F2 and F1 there. So the force that's actually pushing back up on as in opposition to F1, which is pushing down. So this is going to be F2 minus F1. So we know that force is equal to pressure times area, so we can define this as P2A minus P1A, and they're the same A because it's the same object that we're talking about. We can then write this as a function of densities, so we know the density of the fluid. We would want to define buoyant force in terms of that. So then FB is equal to the density of the fluid times GH2 in this case, minus, once again, the density of the fluid times G, and then that is at H1, and this is all times A. Sorry, I dropped my A here. Okay. So I'm actually going to factor this out a bit differently. I didn't mean to drop my A there. So I'm going to say rho FG A times H2 minus H1 is what is equal to my buoyant force. Now, what's really, really important here, and a bit of a jump in terms of understanding, this is actually the volume of the displaced water here, if that makes sense. Hopefully that makes sense. So that's the volume of the displaced water, so I can write this as rho F G VF, where VF, once again, is the volume of the displaced water. And remember, this is equal to buoyant force. So that means that the buoyant force is just equal to the mass of the fluid times G, because density times volume is equal to mass. Okay, so the net force due to the fluid pressure, or the buoyant force is what that's called, is going to be proportional to the height of the block itself. And that's in this problem here. Hopefully it makes sense why that's H2 minus H1, because that's this distance here. Okay. So Archimedes' principle states that the upward buoyant force on an object immersed in a fluid, partially or completely, is going to be equal to the weight of that displaced fluid. So we are going to do a lot more problems with these than you probably actually want to, but unfortunately, that's just how physics goes, and you all know that by now. So we will talk about how to actually apply this when we are doing problems. So let's think about buoyancy. So this is a polar bear here on top of a ball. Okay, it's a beach ball. So if we actually drew a free body diagram of that, you'd have the buoyant force pushing up. You'd have the weight of the bear pushing down, as well as the weight of the ball and the air. Okay, so that buoyant force upward is going to be canceled out by those two downward forces if the beach ball is stationary, meaning that the beach ball is neither rising nor sinking. Okay, uh, the bear is pushing down, so that means that there is a downward force, and then the earth is actually pulling on the plastic ball as well as the air that's actually inside of the ball. So that would be those two forces. These are what are going to balance out the buoyant force, assuming that the ball is not moving. So if we talk about this polar bear, with Archimedes' principle, so the buoyant force on the ball is going to be equal to the weight of the displaced fluid. So remember, that's mass of the fluid times g. So in order to find the weight of the displaced water, we would need to actually know the volume of the water. And that volume of the water displaced by the ball should be equal to the volume of the ball because the entire ball is actually under the water. So if mass is equal to density times volume, then the weight of the water is going to be equal to the following. So let's talk about this, everything that I just said. So we know that the weight of the displaced water is mg. So if you want to write that, weight of displaced water should be equal to the rho v g. Okay, and we're going to talk about this. So rho, this is the density of water. This is the volume of the water or the ball, doesn't matter, same thing because the ball is completely submerged. And then g is just what it is. If we continue with this, we could say, okay, if I don't know the mass of the fluid that's displaced, I can look at this in terms of the density of the fluid as well as if I know the volume that is displaced. So FB, to summarize, is equal to rho F times G times V, which is also just equal to MF, and I'll actually, MFG, sorry, and I'll define all of these things just in case, because I know that this has become a bit complicated probably. So this is the density of whatever fluid that the object is submerged in. Mass, MF, is going to be the mass of the displaced fluid. And then volume V is just going to be the volume of the displaced fluid. That should make sense, of course, because mass, density, and volume are all related to each other. So hopefully that isn't confusing. Now remember, if the object is completely submerged, that volume of the displaced fluid is going to be equal to the volume of the object. So the buoyant force is going to be the weight of the displaced fluid, as we have mentioned already. So the net force that is on an immersed object is going to be the difference between the buoyant force and the gravitational force. So if we have a motionless object, we know that F net should be equal to 0. And that'll be important to keep in mind with all of these things that we end up doing. Is the object actually moving in the water? Is it stationary? Is it not? This becomes a really big thing of force balancing, which I know we had a insurmountable amount of practice with last year. Not insurmountable because we all survived, but it definitely felt insurmountable at times, I'm sure. So buoyancy. So if you've ever been in a pool and you try and push a beach ball downwards into the water, you feel that buoyant force resisting your attempt. So buoyant force itself is not going to be dependent on the object's depth in the fluid, since the only difference in height of the top and bottom is actually going to matter. So where it is in the fluid does not matter. It's the difference in height that matters. Keep that in mind. So as an object sinks, that difference in height is going to remain constant because we don't care that it is going, we don't care about the numerical value of the depth, right? We only care about that difference in height. So both of the orange squares, whatever point that they're at, have the same buoyant force acting on them because once again, the delta H is just the height of the object in this scenario. And so that delta H is not changing because the object is not changing. So that difference in height will not change even though the pressure at that depth will change, but we won't start talking about that just yet. So buoyancy and Archimedes' principle, any floating object displaces its own weight of fluid. So if you have ever been on a boat, the mass of the boat times gravity, so the weight of the boat is going to perfectly balance the buoyancy, which would just be the mass of the fluid, so or the density of the fluid times the displaced volume of the fluid that the boat is actually in. Boats typically go in water, so hopefully that makes sense. And then times g. So if you ever wondered why ships don't sink, or at least shouldn't, it's because their weight and buoyancy force should be balanced, and there's a lot that actually goes into that. Obviously, it's not that simple building a boat, but we have ways of actually doing it such that we create pretty efficient water vehicles. So if we consider an object of volume v naught and density rho naught that's placed in a fluid of density rho f, if that density of the object is less than the density of the fluid, there's going to be a net upward force until the buoyant force balances the object's weight and only part of the displaced volume remains. Okay, so we're going to think about that in terms of how the volumes are actually going to be related to the densities of the object, because that's the important part of what we're talking about here. You displace a certain amount of the fluid. How are those volumes related to the densities? So if we start a derivation here, we could say, okay, buoyant force is equal to mg. So if I take a look at buoyant force, I know that that's the density of the fluid times g times the displaced volume is going to be equal to the density of the object times g times the volume of the object. And I can cancel out g, of course. So then I'm left with rho f v displacement is equal to rho naught v naught. And then I can just get a ratio here such that v displacement over v naught is equal to rho naught over rho f. Okay, so what that relationship is stating is that the fraction of the volume that is submerged is given by the ratio of the object's density to that of the fluid. So that's pretty important. If you were to just figure out what fraction was submerged, so this is the volume displaced divided by the total volume of the object, is just going to be a ratio of densities here. And that's how we talk about specific gravity. So we'll go on to that next here. So the ratio of the density of a substance to that of a substance, to that of a standard substance is known as specific gravity. So the standard substance that's almost always used is water when it's at its densest, which is at 4 degrees Celsius, and it has a density of 1,000 kilogram per meter cubed at that temperature. So we define specific gravity once again, and I might just write that as Sg. Equal to rho substance divided by rho water. Now, specific gravity is not always talked about in AP, but I do think it's a really important concept in terms of understanding how to actually figure out how these things are related and to see how different pressures and uh, or different volumes and densities are related and whatnot. So a substance that has a specific gravity of less than 1, this should say, sorry, less than 1, means that it is going to be less dense than water and would flow on water. So for example, oil is going to float on water and therefore its specific gravity should be less than 1, again, assuming a constant temperature. Um, and then a substance that has a specific gravity that's greater than 1 means that it is more dense than water and is going to sink in the water. So this is always going to be a ratio. Specific gravity does not have units, okay? So if it's less than 1, it is less dense than water. Greater than 1, more dense than water. So if you were to look at these different objects, you could compare the densities just by looking at how much of the block is actually submerged while it's floating. So if we look at block A first, block A we would say is about 25% submerged in water as it floats. So therefore its density is 25% of that of the water because again it's 25% submerged. That means that its density is 25% of that of water because it is floating here like this. Okay? Block D is fully submerged, however, it is stationary, so that means that it has to have exactly the same density as water. So it does not sink, it is stationary there, so D has the same density as water. You could use that method to compare the densities of various objects to liquids that aren't just water. It can really be any object or any fluid rather that has a density. Okay, it's just that 99 times out of 100, the problem that they give you is going to pertain to water. Again, specific gravity is not asked about that much, but it's a really nice tool to have if you're looking at this and you could say, okay, A is 25% submerged. That means that its density is 25% that of water. And we're always trying to get relationships between things rather than necessarily plug in a bunch of numbers. So I think that specific gravity is quite a helpful tool. Okay, so now we'll do some examples. So 3 objects of the same volume but different materials are completely submerged in water. They are zinc with a density of 7,000 kg per meter cubed, nickel with a density of 8,900 kg per meter cubed, and silver with a density of 10,500 kilograms per meter cubed. Which of those has the greatest buoyant force exerted on it? So, if I look at the problem, I'm told in the beginning they are completely submerged in water. So that means that they all have the same buoyant force. This goes from looking like a problem that is quite complicated to actually being quite easy because the buoyant force is only dependent on the displaced fluid. It has nothing to actually do with what these things are made of, right? So if they are all completely submerged in the water, that means that all of the volume of the water for all of those cases is the same, and therefore the buoyant force on each one is the same. A metal sphere weighs 5 newtons in air and 3 newtons when it is submerged in water. What is the buoyant force on the sphere when it is submerged in water? This should be pretty straightforward, but I'm going to draw it for you just so we have a picture here. So if I look at this, I say, okay, let's say I have some container of water, right? And I have, when it's in air, it's 5 newtons pushing down. When it's submerged in water, there's 3 newtons pushing up. So what is the buoyant force on the sphere when it's submerged in water would be just 5 newtons minus 3 newtons should be 2 newtons. An object has a volume of 2 cubic meters. What is the buoyant force on the object when it is completely submerged into the water? Once again, assuming that the density of water is 1,000 kilogram per meters cubed. So we are looking for buoyant force. We know our equation for buoyant force, FB is equal to rho Vg, where rho is the density of the fluid, V is the volume that is displaced. So we are told that the object has a volume of 2 cubic meters, and we're told that it's completely submerged. So that means that the volume that's displaced is equal to the volume of the object. So we can plug in this 2 cubic meters for the volume of water that's actually displaced here. So this ends up being 1,000 kilogram per meter cubed, 2 meters cubed, G. Hopefully that makes sense. So completely submerged is a really big key here to know that the volume of the object is going to be the same as the volume of the displaced water. We'll do a couple more examples and then we'll be done with this lecture. Of course, we had to come across our friend tension, because tension simply will not go away, but luckily tension will only be in one dimension in this unit, because the only dimensions that we care about in fluids as far as the forces are up and down. We do not look at side to side because that becomes a much more complicated problem, so we will not look at that. So an object is submerged in water, so once again submerged in water, so I'm going to write this right away. The volume displaced is equal to the volume of the object, and is attached to a rope as shown. So if the specific gravity of the object is 0.8 and its volume is 0.02 meters cubed, what is the tension in newtons in the rope? So if the specific gravity is 0.8, we know that specific gravity is equal to the density of the object divided by the density of the water. So that means that the density of the object is equal to 0.8 times density of water, which is going to be 800 kilogram per meter cubed. Okay, so that's important to know. That's for our object here. Okay. Now let's look at the actual forces that are acting on this. So we know we have buoyant force pulling up, we have tension pulling down, and we have the weight of the object also pulling down. Okay. So if we look at this, we could say, okay, we're solving for the tension. Tension is going to be equal to FB minus FG. And we know that FB is equal to the density of water times the displaced volume of water times G, minus, very similar for the object, which we're writing it in terms of densities and volumes, obviously, because we don't know the mass. Remember that mass is equal to rho v. I know sometimes I jump ahead with that, and I apologize. I just assume that we know this relationship and why I'm doing Fg as this by now, but I'll make sure that I make that a bit more clear. We know that the volume of the water is going to be equal to the volume of water that's displaced is equal to the volume of the object, so V displaced is equal to V object. I'm going to just call that V, okay? So this becomes rho water, Vg minus rho naught, or object, I really should say, V object G is equal to the force of tension. So force of tension is equal to Vg times the difference between these two densities. So we're told in the problem that the object has a volume of 0.02 meters cubed times G. And then we just take a difference in the densities. So we have 1,000 kilograms per meter cubed minus 800 kilograms per meter cubed, and that's just 200. So when you calculate this out, I got cut off on my PDF here, so give me 1 second to calculate it. you will get an answer of 39.2 newtons. Okay, a couple more examples, 3 more. That one's definitely the longest of the 3 that we just did, I'm pretty sure. So example 5, a 1500 Newton object floats in water. What is the weight of the displaced water? So it's floating in the water. That means that the net force is equal to 0. So the buoyant force minus gravitational force is going to be equal to 0. So we know that the object has a weight of 1500 newtons. So that means that buoyant force must also be 1500 newtons. So this is the example of when I told you about a boat floating in water, that the weight of the water that's displaced has to be equal to the weight of the boat. A small empty rowboat with a mass of 48 kilograms floats on water. What is the volume of the water that it displaces? So this is a bit different from what we've done. Same idea, but now we're actually solving for volume. So I know that I can figure out buoyant force because I have this mass of water. So buoyant force is equal to the weight of the fluid. So that's the mass of the water in this case times g. So 48 kilograms times 9.8 meters per second squared. So this is 470.4 newtons, and we will use that. We'll come back to that. Okay. So I know that this rowboat has to, the weight of the buoyant force, if it's floating, has to be equal to the weight of the boat itself. So the weight of the boat I know is rho v g is equal to this 470 newtons, 470.4 newtons that I just found. Okay, so then I can rearrange and solve for V. So V is equal to 470.4 newtons. Density is of water, so this is 1,000 kilograms per meter cubed times 9.8 meters per second squared. Okay, and that will give you 0.048 meters cubed. And I think I said this backwards. I was saying this is of water. I apologize. This is of the boat. This should be boat. Sorry about that. I was wondering why I used a density of 1,000 in the next one. So this is the mass of the boat. I'm sorry about that. So buoyant force. Remember that buoyant force is going to be equal to the weight of the object, because it's floating. So we know FB minus FG is equal to 0. Okay. And Fg here I've just defined to be this of the water, and the buoyant force is the same. You could have done it either way because they're equal. It really doesn't matter, but I do apologize that I misspoke on that one, but hopefully my correction makes sense, especially because the density of the boat is not 1,000 kilogram per meter cubed. An object floats on water with 3/4 of it submerged. What is its specific gravity? So again, we talked about this relationship. So if 3/4 of it is submerged, that means that its specific gravity is going to be 0.75. Hopefully that just makes sense. When we talked about the 4 blocks that were in water, so block A was 25% submerged. That means that it has 25% of the density of water, which just means that rho object over rho water is going to be equal to 0.25. So remember, specific gravity is of the object or substance, whatever you have, over the density of water. That is it for this lecture. I know this one was a bit longer, a lot more to write down in this one probably, but hopefully we will not have too much to do on the next 2. I think this is one of the longer ones, so yeah, the next one will be a bit challenging as well, but I think the last one is the shortest of all of them. Yes, the last one's only 8 slides, so next one will be a bit rough as well, but we will get through it, and we will start that shortly.